yesterday's session. Then I'll start with the new chapter waves. Let the theory of wave, let it go on, because last period you will once again switch over to oscillation and complete the numericals. I think that would be better. So what was the last one was? Was it acceleration? We have to complete acceleration, I think so, right? This is what we did last class. 11B. Only 19 right now. B, just check. Can you see the slide presentation?
Yes, ma'am. Now we can. This is the last thing we did. Yeah.
Okay, fine. Need to wait for. Aaron. Abel, Austin, Abhishek. Abhishek. Derek. Dheeraj. Dheeraj. Adil. Hitesh. Jatin. Jatin. Johan. Jonathan. Kritya. Who is Maheshwar? Minus. So your velocity at any instant is a omega cos omega t. We'll go for your acceleration. Was velocity was a omega cos omega t. So acceleration will be d by dt of v. So a is equal to d by dt of a omega cos omega t. Right, boys? A omega is a constant. The amplitude of the wave and the frequency, angular frequency is a constant. So let me take a omega outside the differentiation cos omega t. So when you differentiate cos omega t, you will get this as minus omega sine omega t. Correct, boys? So your acceleration becomes equal to minus a omega squared sine omega t. So now in this expression, we have to replace omega as 2 pi by t. Was we need to replace omega as 2 pi by t. What is the time? The time is 2 by, is it 2 by 3 of a second? Boys, is that the same value correct? You have to check. Dheeraj?
Ma'am, it's 1 by.
Ma'am, I think it's 1/3.
Okay, 1/3. Fine. What about your time period? What about the time period? Hitesh, what is the time period? What is the value of the time period? Hitesh? Austin, what is the value of the time period? Austin? Austin is in class?
Yes, ma'am.
He responded, okay. Time is equal to 2 seconds. What is the amplitude of the wave? What is the amplitude of the wave? Is it 5 centimeter?
Yes, ma'am.
Fine. Now you substitute in this equation. So your acceleration becomes minus a is 5, omega is 2 pi by t the whole square, sine of omega is 2 pi by capital T into t. Now you substitute the values. Now get me the answer in terms of pi. I think so you can substitute. Get me the answer, boys. Derek? Derek? Derek, are you in class? Okay, what's the answer now? Minus 5, 2 pi by 2, sine of,
Ma'am, is the answer negative 5 pi square?
yeah, 2. This is 1 by 3. So 2 and 2 will get cancelled. So A becomes minus 5 pi, so 5 pi square, sine of, what is pi by 3? Pi by 3 is 60 degrees. So there is minus 5 pi square, sine 60. What is sine 60? Root 3 by 2. So minus 5 pi square into root 3 by 2, it is centimeter per second square.
Ma'am, for meter per second square, we just need to multiply.
10 to the power of minus 2.
Okay, ma'am.
Please 2 seconds. I'm substituting for this. Was your omega, we are substituting for omega squared as 2 pi by t. Omega as 2 pi by t. Copy down, boys. So we have substituted, was in this equation, I have substituted A as 5. Just differentiate. So omega squared as 2 pi by t. 2 pi by t. Then we substitute this t as 1 by 2. Have you completed, boys? Abhishek? Abhishek? Boys, once you have completed, let me know so that I'll start with the next chapter, waves.
Isn't it the same chapter? Waves and oscillation.
Waves and oscillation, same unit. Units are the same. It comes under the same unit, but it has two chapters. Waves,
Yes, ma'am.
oscillations, and then waves. Boys, shall I move for the next one? 11B.
Yes, ma'am.
Fine, I'll just close this point. Boys, you can start with waves. The numericals, whatever we'll proceed in the last period, you can copy it down at the last page of your notebook, just putting a subheading. Just start with the next chapter, waves. You know what is a wave, right? So when any energy enters into a medium, suppose you have a solid, if heat energy travels through the medium, now what does this heat energy is capable of doing? It makes the particle of the medium to vibrate. So it disturbs the medium. The propagation of this disturbance is called as a wave. So when a wave travels through, when an energy travels through a medium, it makes the particle of the medium to vibrate, or in other words, it disturbs the medium. And as the wave progresses, the particle keeps on vibrating. So the propagation of this disturbance, we call this as a wave. So we just started with a wave. In this chapter, what are the things that you will be learning as per the revised syllabus, as well as what this revised as well as a deleted topic. First one, you'll be learning about transverse and longitudinal waves. Then you'll be studying about the speed of a traveling wave, displacement relation of a progressive principle of superposition of waves. Now, this is a very important topic. This will be carried over to optics in grade 12, optics in grade 12. Then you'll be studying about reflection of waves, then standing waves in strings and organ pipes, and finally beats. Beats is only the qualitative idea. So these are the topics which will be for this entire chapter. So we'll start with transverse and longitudinal waves. Right, boys? Waves.
Ma'am, after the numericals, you have to do this.
Yes, boys, you can continue with this because numerical, I felt last period would be wise enough to do numerical rather than theory. 11B, as what mathematics teachers is also stating, that you people are not, boys, whenever you are being called, even if the answer goes wrong, we don't want whether the answer is correct or wrong. We just want to check whether you are interacting or not. If I have to call a student, I need to wait for 2 minutes. The same thing mathematics teacher is also reporting. Let the answer go wrong. You need not worry about it. It's not whether your answer, what you answer. So any question, what you answer is correct or wrong. It doesn't matter. It only matters whether you're interacting or whether you are in class. Transverse wave. Yes.
Did we have to write the previous slide? What's the wave?
No need, boys. No need. No need. Writing part you now minimize. Wherever is required, I'll tell you where you need to write. Right. So transverse and longitudinal waves. Only the introductory part will start because you have already learned in grade 9. So I'll call Jonathan. Jonathan.
Yes, ma'am.
Okay. What is a transverse wave?
Ma'am, I'm not really sure, ma'am.
Okay.
There are two types of waves, transverse and
Mm.
longitudinal.
Mm.
One of them is it has areas of concentration and areas where there's less amount of the matter. So
Sure,
one is
sure.
called
That
a
is
rarefaction,
correctly
and the other one is called a
correct.
compression.
Yeah,
I
that is
think
you are
that's
talking about. You're
longitudinal. I
talking
don't remember
about.
the other one,
Sure.
ma'am.
No, that's correct. Correct. What you're saying is correct. Good. That is what we call it as longitudinal waves. Then comes your transverse wave. Now we'll see, boys. What is a transverse wave? What is a longitudinal wave? Thank you, Junaid. Now, a transverse wave. Suppose transverse wave, for example, all your electromagnetic waves, your light waves, light waves, infrared waves, that is heat radiation, ultraviolet waves, then you have microwaves, then you have X-rays, gamma rays, very intense gamma rays. Now these all form electromagnetic waves, which means these are the waves which travel through the medium with the speed of light. Now, what is the character of such transverse wave or EM waves? They make the particles of the medium to vibrate. Now, in which direction? Suppose the wave is propagating, the transverse wave is propagating along, say, positive X direction. Then this wave is capable of making the particles of the medium to vibrate in a direction perpendicular to the direction of the wave propagation. The wave is moving along positive X direction. Now, what does this wave do? It disturbs the particle of the medium. It makes the particle to move up and down about the rest position or the mean position in a direction perpendicular to the direction of the wave propagation, which means the particle has to move, vibrate along positive y-axis and negative y-axis in a two-dimensional plane. So the particle will vibrate up and down about the mean position. Such waves, we call them as a transverse wave. The character of a transverse wave characterized by crest and trough. Then you know what you mean by the amplitude of a wave. Now, what is meant by wavelength of a wave? Johan, what is the wavelength of a wave?
Yes, ma'am.
Okay, wavelength of the wave is the distance between two consecutive crests. Can you see those markings? This is a crest, this is a crest. So the distance between any consecutive next to next crest, we call it as the wavelength of a wave. It can be the distance between any two trough. Right? In a transverse wave, you will have crest and trough. The distance between adjacent troughs or the distance between the next to next crest, we call it as a wavelength. And what is the amplitude of a wave? The maximum displacement of the particle. The particle is going to vibrate up and down. The maximum distance to which the particle is going to vibrate, either in the upward direction or in the downward direction, we call it as the amplitude of the wave. So what do you mean by the wavelength of a wave? It is the distance between two consecutive crests or two consecutive trough. It's called the wavelength of the wave. Johan, can you repeat what is meant by wavelength of the wave? Johan? Johan? Jopal, what do you mean by one complete oscillation or one complete cycle? What is one complete cycle?
When it completes a full rotation.
Okay, it completes one full. Suppose the particle starts from this point E, right? It comes back to the same position. Your point E lies along x-axis, so it comes back to point F, which also lying along x-axis, going up and down. That is called one complete oscillation. In terms of a simple pendulum, if you start the pendulum from position B, right? If the Bob goes to position A, comes back to B because of inertia, it overshoots, and again when it comes back to B, that is called one complete oscillation. What do you call the time taken to complete one complete oscillation? Can someone answer? What do you mean?
Time period.
Time period. Time period is the time taken for one complete oscillation. So all these things you have learned in grade 9. So transverse, this is all about your transverse wave. So always the particles of the medium will vibrate in a direction perpendicular to the direction of the propagation of the wave. Fine, boys? And then you studied about amplitude. Yes, you have studied about the wavelength of a wave. Then what is one complete oscillation and time taken for one complete oscillation. Next we'll go for longitudinal wave. So what is longitudinal wave? Suppose when the sound wave, especially your sound wave, is a longitudinal wave. Now when sound wave enters through a medium, say it is going to enter through air. So your air molecules become the particle of the medium. Now in which direction will the particle move? Suppose the disturbance is traveling along positive x-axis, the particles of the medium will move to and fro about the mean position. It goes to positive x, it goes to positive negative x-axis. So it moves in a direction parallel to the direction of the propagation of the wave. If the wave is traveling along x-axis, the particle will move in a direction parallel to the direction of the propagation of wave. It means it moves positive x and negative x. So it's always in a direction horizontal to the direction of the propagation of the wave. In case of your transverse wave, the particles will move perpendicular to the direction of the propagation of the wave. Here they are going to move in a direction parallel to the direction of the propagation of the wave. Now, you are very familiar with the characters of a longitudinal wave, compression and rarefaction, which means when your sound waves travels through a medium, at some point the air molecules are compressed, at some other point the air molecules are relaxed. So wherever, which means you will have alternate compression and rarefaction, right boss? At some point the molecules will be compressed, at some other point the air molecules will be relaxed. So the portion where your air molecules are being compressed, there the pressure of the medium as well as the density of the medium is higher compared to the region where the particles are being relaxed. In the region of relaxation of particles, the pressure and the density of the medium is less. In region where the particles are being compressed, the pressure and the density of the medium is higher. Are you clear, boys? 11B? 11B?
Yes, ma'am, we are clear.
Okay.
Yes, ma'am.
So okay, the distance between next to next adjacent compression, or the distance between next to next rarefaction, we call it as the wavelength of the wave. So all this you have studied in grade 9. Just we went through these two. These are the two types of waves, especially sound waves. Longitudinal wave, example of longitudinal wave is sound wave. For transverse wave, you can have the other two example. So the wave which is going to travel through a stretched string. All your instrument, right? Stringed instruments will have strings stretched, right? Only the string which is under tension will vibrate. So the waves that move across a stretched string, when you plug the string begins to vibrate, where the particles of the medium will going to vibrate perpendicular to the direction of the propagation of the wave. So one example of transverse wave is the wave that travels along stretched string. Right? And same way, the waves which propagates water waves on the surface of water. So that is also a transverse wave. All your electromagnetic radiation are an example of transverse wave. a new concept which has to be introduced apart from what are the character of a wave? How can you characterize a wave? Let me know. Boys, your audio system, tuning system in your automobiles, in your cars, you have a tuning system where you take up the signals. Suppose if I want to catch a particular channel, I want to hear something from a particular channel. Now, how do you characterize? What characterizes? You have a tuning system, right, boys? In your cars, now that you don't have a knob, but you have those switch keys. Now, how do you select a station?
Ma'am, the frequency.
Frequency, yes. Any general frequency you generally hear? I don't know. I'm asking you, boys. Any particular stations which always comes into a mind which has a frequency? 101.1 MHz. Is this the channel you are hearing? Was you hear, right? When you're traveling,
Yes, ma'am.
don't you
Yes.
hear? Okay, any channel you particularly hear will be characterized by a wave because you're picking your receiver is picking a wave. A station means whatever is audio waves are being broadcasted, it has a particular wave or the wavelength or FM waves, AM waves. Have you heard about this? Have you heard about this?
Yes, ma'am.
Frequency modulated wave, amplitude modulated waves, right? This is how your transmission, electrical transmission happens. You are characterizing a wave by means of its frequency, by means of its amplitude. In your radio station, which are the waves which is being characterized? Is it FM waves or it is AM waves? Frequently, which one you are using?
FM.
FM waves, yes, frequency modulated wave. The frequency of the wave is being increased by what we call it as a carrier wave. That process of mixing, we call it as modulation. So any wave for that matter, it is characterized by frequency. Then what else? You studied in your grade 9. What else, boys? What is the other character of a wave? Frequency. Then what else you have learned in grade 9? Just recall. Just recall.
Ma'am, isn't amplitude a character as well?
Yes, correct. Yes, amplitude. Fine. Next.
Ma'am, is speed one of them?
Yeah, speed also. Correct. Speed, frequency, amplitude. Then what? Just when you think of a wave. Yes.
Ma'am, wavelength.
Correct. Wavelength. These are all the characters of a wave. If the frequency is right, if the frequency of the wave is very high, then what we call it as the pitch of the wave. Have you heard about the pitch? The sharpness of your sound depends upon the frequency. It was. So these are all the characters of a wave. And you know about wave equation? Wave equation, the basic one. Boys, please don't think that your waves, whatever you are studying right now, it is only, what else we can say? It is only constrained to acoustics. It is for wave optics. Later on, if you go for your electrical engineering, this becomes your basic, how you transmit waves. Telecommunications. For satellite communication, which waves are you using? You have electromagnetic waves. Which type of wave you use for satellite communication? 24/7, you're with your mobile and laptop. Was? Which type of waves are you using? 24/7 with mobile, 24/7 with laptop, but you don't know what type.
Wi-Fi?
Okay, but what type of waves? The mode of communication, right? Suppose, yes, boys?
Radio waves?
Radio waves. Okay, if I'm using radio waves, boys, if you're traveling from Dubai to Abu Dhabi, right? when you switch on your channels, as at some point you will not receive the signals, because those stations are broadcasting the audio signal to radio waves. Radio waves will be reflected by your ionosphere, your radio waves. Suppose you have a station, right? Now this station is releasing its audio signals now in form of radio waves. Now what happens is that this radio wave will be reflected by your ionosphere. So the reflected wave will be picked up by your, say this is a transmitter. The station is going to transmit through antennas. The audio signals are going to propagate through your atmosphere as radio waves. Your ionosphere will reflect it. So your receiver will receive this. Okay. But the problem here is that the range is very less. You know what is the range? Are you clear, boys? The range from your transmitter to your receiver, the distance is, you can have certain meters, so kilometers, but not beyond that. So radio waves are not popular for long distance transmission. That is why you use your satellites. So you use your satellites so that if the from one part of the world, if your transmitter is, say, from one part of the continent, you can go to the other part of the continent, you can receive. So you have satellites. Here, what type of waves the transmitter is going to transmit? Audio and video signals. What type of waves? You have GPS, you know all about this. What type of waves are you using, boys? Microwaves, okay? Fine, boys. Microwaves are the waves which can penetrate the ionosphere, reaches the satellite. Now your satellite, your geosynchronous satellite, almost 30,000 kilometers above the Earth's surface. So when the object is at a greater height, when it is going to reflect all your microwaves, the entire globe can receive, any point on the globe can receive. That is why for your telecommunications, we use geosynchronous satellite. For other purpose, like for if you want to check whether for weather forecasting, or if you want to check the mineral deposit on the surface of the earth, then those satellites have to fly. Even for military purpose, we use satellites. Those satellites needs to fly at a low range. Those are called polar satellites. So for all your telecommunications, you need to go for your microwaves. For radio, audio broadcasting, short range distance transmission, you can use your radio waves. Fine, boys. I have to start. Thank you.
Thank you, ma'am.
Thank you, boys.
Thank you, ma'am.
Thank you.
ma'am.
Thank you.
Thank you, ma'am.
Thank you, boys. So